and yeah, a few different variations of applications. But yeah, you can check us out as well at OAVG Auto Autonomous Vehicle Group.ca.
Thank you, Nick. Yeah, a few words about the Stuttgart chapter. It's an autonomous driving meetup that I founded 2017 after finishing the Udacity self-driving car engineer nano degree. And what is the similar thing about all of us? We all met in parking lots, and that's why when the pandemic started, we had the idea and shared that with the Oakland meetup to have a joint meeting and a joint race, autonomous racing in the simulator. So that's how the parking lot nerds came into play. And before, we met at the Maker Faire and at several events. So it's quite an active community. And well, and as we competed for the IROS 2020, we even used some of the code of the TU Munich for calculating the optimal race line, and that's why we became very interested in your repository, Alex, and your team. And well, to end there, we are really thrilled to have you here today, and yeah, looking forward what you tell us about what is behind this amazing race we saw all on the Indianapolis Motor Speedway. And yeah, let me hand it over to you, and the stage is yours. Thank you.
Right. Thank you, Rainer. Thank you, Alex. Thank you, Nick and David, for the invitation first and for the introduction you already made. I just take over that chance and introduce myself very briefly. I'm Alexander Wischnewski, and I've been around racing cars since the very beginning of my studies. So I started with Formula Student Electric in 2014 and 2015 at the DHBW Stuttgart team. So the Formula Student is a design competition where students actually build a race car completely from scratch. At that time, that wasn't autonomous. That wasn't such a big thing there. It's now already 7 years ago. So, but after that, I joined the Technical University of Munich in 2017 as a PhD student, and we started working with the company Bareiß. So we ran several autonomous racing demonstrations with Bareiß in 2018 and 2019. We've been at the Formula E event in Berlin. We've been at various F1 circuits around Europe. So that has been something which has been around for me from the very beginning. The team was founded by 4 PhD students at the chair of automotive technology and the chair of automatic control at Technical University of Munich. It has been quite a small team in the beginning, but with early successes, we were able to grow the team and take on harder challenges and expand our activities towards more complex situations. So the team is now around for 4 years. It has grown up to 15 PhD students and about 30 to 40 bachelor and master students. So in addition to actually doing some of the research we are doing on those prototypes, we also see those racing competitions as a strong opportunity for the students at TUM to engage with the technology and work in actually really close to real projects. So they come into touch with all of those things you need: version control, using Linux, using Docker, using all those tools, using ROS. And that's just a great challenge, despite only writing your bachelor or master thesis. And you're part of a bigger team. And I think I'm not revealing too much if I can say that actually also some of that code has been running in Indianapolis. So that's just a great chance for people already early on in their studies to join our team. So often it's said the TUM team is made up of PhD students, but I think that's not entirely true, or that's only half of the story. So we're really a huge team with people from a variety of backgrounds and a variety of progress in their studies. So it's already possible to join us very early on. All right. Having said that, I think I'm now going to dive a little bit more into the actual topic of the talk. So the Indy Autonomous Challenge, and the subtitle here, A Different Approach to Autonomous Driving, is motivated by the fact that we believe that there's actually value which you can take from racing at a circuit towards autonomous driving on real streets. So that's not only an educational exercise, but there are a ton of technological challenges you can take over and actually apply in the real world. I'm just going to show a slide, a small video for introducing the Indy Autonomous Challenge. Apparently, we can't share the sound, so you have to imagine that. But this video gives you a pretty good idea of what the Indy Autonomous Challenge is all about.
Alex, your microphone is muted. I don't know if you can hear us. And also, I think Joe is is waiting to get in. Alex,
is it the right one? I don't see anybody.
Guys, you're live on Twitch.
All right. Come on. That has been a pretty good overview. What we planned for, what we targeted. So the challenge was set out in early 2020, where Energy Systems Network, a small nonprofit company in Indiana, invited universities from all over the world to compete in this unique and first of its kind autonomous race car challenge. So what has been different to previous challenges, I think there are two main things. The target was always to build at least 10 race cars. That's something we definitely achieved. So you can see on the right picture, it has been 9 in the end, but we built the biggest group of autonomous full-scale race car which has ever been designed. And they set out a $1 million prize for the team, which is advancing autonomous technology the most. So we'll see a little bit later on of how the challenge actually turned out and what the competition has been in the end. But it has been started in January 2020, just shortly before the pandemic hit. So one of the major challenges, despite actually racing autonomous, we had to deal with was the fact that basically the first year of the Indy Autonomous Challenge was basically pure virtual. So while actually having some disadvantages, this also gave us the chance to actually practice our virtual design workflows, our remote collaboration workflows, and it allowed us to start working with many of the other international teams already prior to the race. There has been a variety of hackathons where the teams had to solve specific challenges in a simulated environment. I think that's pretty similar to what this community does from time to time. So it started with driving fast laps and then race head-to-head with one other car, up to a full-blown simulation race where up to 8 cars have been racing each other autonomously all the time. There's obviously not enough time to share footage of all of that here, but if you look for the ANSYS simulation race of the Indy Autonomous Challenge at Google, you're going to see a fully produced, I think, 35, 40-minute video of that event. And it has all the footage you need if you want to dive deeper. And there has been some pretty nice head-to-head racing. Obviously, in simulation, everyone is a little bit more eager to go for a risky tuning of its algorithm. So yeah, some pretty decent racing of multiple cars at the same time at the end of simulation race. So I just started saying that we believe there's a lot of stuff you can take from driving at the racetrack to driving on classical streets. So I think the two most prominent things, despite the actual skill set and know-how you do acquire, is first that the reaction times you have to have on a racetrack are really, really low. So the racetrack forces you to develop algorithms which are really responsive to what's going on the outside, and at the same time considering very complex situations. So it forces you to develop probably the most efficient algorithms which are out there in a very short time. The second thing is that the racetrack is an inherently unstructured situation, and what that means is there are no traffic rules. There are some loose rules of engagement. So obviously you're not going haywire and directly hitting your opponent. But despite that, the rules on the track are pretty open, and it's basically about going to the start finish line the fastest you can. And that forces you from a development perspective to actually work on topics like behavior understanding, having complex data, behavior prediction models, and having planning and control models which can actually work with those dynamically changing scenarios. And that's something when you drive autonomously at the racetrack, you can take to the real streets, because if we look here on the right, obviously this situation is more structured, and there are like lane markings, traffic rules you can follow. You could use high definition maps. You can look at traffic lights. But those approaches are all prone to, let's say, being fragile in the face of the long tail of autonomous driving. So in all those edge cases which are present, construction sites, broken traffic lights, emergency vehicles, all those situations actually require you to have some real understanding of what's going on. And we do believe that practicing on the racetrack forces you to actually develop that understanding, and then those technologies can be taken to the real road. Obviously, there are some modifications needed because you probably don't want to like dismiss all the traffic rules in terms of speeding. So there are some rules you have to add, but we believe it's easier to add them afterwards instead of relying on them on the very first instance. So that's basically a summary of what I just presented. There's one more thing here to add, and that's the operation at the limits of vehicle dynamics. And that's another thing. At a racetrack, you corner, you accelerate, you brake, always at the limit what the vehicle can do. And that's something which is obviously not required in day-to-day driving, and therefore also leads to quite rare but also quite dangerous situations. For example, if there is a sudden accident in front of you, many people are not trained to do an emergency brake maneuver safely. And we believe that developing those algorithms at the racetrack gives you a chance to actually improve already driver assistance systems, but also in the long-term autonomous driving cars to handle those situations better, because there are algorithms out there who can do it on the racetrack. So it should be possible to do an evasive maneuver and a safe braking maneuver at the very same time, which is probably hard for most of us because we maybe face those situations once in a lifetime, or maybe twice, or maybe 5 times if we go to practice it somewhere. But getting the knowledge you have if you run on the racetrack, that's a completely different thing. All right. Having said that, from the motivational point of view, I want to introduce you to that race car which we have been running. This race car has been provided by Delera. It's a modified Indy Lights chassis. So the chassis, the suspension, the aerodynamics, that's all standardized for all the teams. And in addition, it's the very same as the Indy Lights series run. So we had one of the best chassis manufacturers in the world working with us here. The car was designed by the Clemson University in the Deep Orange program, together with all the sponsors you can see. So just to name a few, I think many of you know Schaeffler, which has been providing the drive-by-wire system Space Drive. There has been AD-Link, who have been providing the compute hardware. Hexagon has been providing us with GPS and radars. There has been Luminar, who provided us with the LiDAR sensors. So all sensors, LiDAR and radars and cameras have been set up to show 360 degrees of field of view around the cars. So the cameras has been provided by Elliott Vision. So you see there's a variety of company sponsors who have been working with Clemson University and later on with us to make all of this possible. The race cars have been brought together by Junkos Hollinger Racing. So we had a professional race team on site, which was supporting the race vehicles. The teams had the chance to focus on developing the software or the software side of the racing car. So obviously, we have been working also to make like drivers run, so sensor drivers, not actual race car drivers, and all these things. But there is so we could focus on, let's say, the software side and put all our efforts in there. So that has been the hardware. That has been the same for all the teams. So I think now here comes what is a little bit of our secret sauce, or that's the software architecture. I'm going to guide you through this in the next 5 to probably 5 minutes, as I want to take the chance to explain some of the choices and the reasoning between just behind of what is here. So we decided that we want to use as many sensors as we could. So we didn't want to focus on a single sensor and maximize that. Instead of that, we decided that we're going to use as many sensors as we could. On this architectural slide, you're going to see all 4 sensor modalities, so GPS, LiDAR, camera, and radar. But I have to already mention here that we didn't use camera in the final race. That has been a decision which was made due to resource constraints. So we were able to drive with GPS, LiDAR, and radar, but we didn't have enough time in the end to actually bring all 4 sensor modalities to work. So we collected all the data with the cameras, so we hope that we can refine our algorithms there later on and improve that for the next race. But for all you're going to see now, it has been GPS, LiDAR, and radar to run that autonomous race car for us. So how's that working? On the localization side, we use a mix between GPS and LiDAR-based localization. So we can actually build a redundancy. There has been 2 GPS receivers. It's pretty good to run with GPS on racetracks as long as you have RTK corrections. So that's something also, again, from a resource point of view, we didn't want to put too much resources into that topic and decided to run mainly from GPS and use LiDAR only to verify or sanity check of what's going on. From an object detection point of view, we had the approach to actually diversify ourselves here. So we decided that we want to operate 2 distinct LiDAR pipelines. So the first has been a deep learning-based pipeline, which is giving us the chance to actually train the algorithm on the data which we got from the tests and from the race cars. So that algorithm was really targeted in detecting specifically race cars. Second thing was clustering algorithm. And that algorithm was, let's say it was the general algorithm in the stack here. So the target was not only to detect race cars, but also to detect other obstacles which might be there. So for example, debris, which is on the track, or just for instance, if, for example, a tire would be lost by a car, such that we can still detect these things. The third, here again, a deep learning-based pipeline based on camera. So I'm going to explain a little bit more in detail what those algorithms could look like. And all those results have been going together into what we call object tracking, together with the radar, which is directly giving us the fused objects, and so we don't have to really post-process that. Having that object tracking there, so it's fusing up to 4 different like 4 different detection pipelines. One of the key challenges there is to synchronize all of them to compensate for different perception times, for different processing times. That has been a key challenge. So that's the main task of the object tracking. So fuse all those information and provide that as a single cleaned up database to the next step in the pipeline, which is a prediction algorithm. So that prediction algorithm is, it's basically doing what's its name says. It's predicting what's going on. So for each car which we could detect, we have a prediction for up to 5 seconds what our race car thinks that other car on track or that other object on track is actually going to do. That could also be a prediction that that car is static or that object is static, but it's doing that based on the last observations which are filtered by the object tracking. All those information are fed into the planning module. This planning module really combines all the information which are there. So that's the race control information. So for example, if there's a yellow flag or a green flag, that's information about what we think is the maximum possible vehicle performance. So maximum acceleration, maximum speeds the car can go. And there are information about what's probably the best race line on the track. So that the car don't have to recalculate that all the time, and it can refer to that race line and already know that that's a global optimal solution. All those information are fed into our what we call local trajectory planning. So that local planning is actually taking into account all those different cars, all those different objects which were detected, the predictions of all of that, and is then calculating the best solution for our race car to proceed. So that solution covers a 5-second approach, a 5 seconds time duration. That's pretty long, but if you run at high speeds, that's what you need. So because, for example, if there's a static object in front of you, you actually have to properly brake and then evade. And those maneuvers take quite some time because if you drive really fast, you can't just instantly decelerate the car from 280 kph to 0 or to very slow driving speeds. There's a redundancy here. So that's what we call safety assessment. The basic idea here is that this algorithm helps us to verify that the trajectory planning is operating as intended. So it's taking all the inputs to the trajectory planning, and it makes sure that the trajectory planning produces a solution which is compatible to all the constraints which are in this which are made by, for example, objects, track balance, acceleration limits. And the key idea here is that it's much easier to actually check that solution rather than producing that solution. So with very little coding effort, it's possible to build not really a redundancy, but a redundant check system, which is monitoring that the algorithm works as intended. And this functionality is especially important during testing because it allows you to stop a maneuver before something bad happens. Finally, all those information is going to the control module. The control module consists of what we call state estimation. So that fuses different localization options, the inertial measurement units, wheel speed, steering wheel angles, and everything to obtain the best pose and the best velocity estimate and the best acceleration estimate we can have from the car. And all of that is going back to a tube MPC. What this tube is, I think we're going to see that a little bit later on. The important part here to take away is that we're running an MPC-based controller. And the key reasoning here is, so that's much more complex than running, for example, a pure pursuit or like a classical lane keeping PD controller. But why we need this here is that our local trajectory planning is more like a course planning. So that's a graph-based planning. And it's basically, it's like resolving the ambiguities in the situation, and it's planning a course path based on splines. But these model predictive control methods are really good in smoothing that path and like actually preventing short acceleration spikes and these things. So we combine the strengths here of graph-based methods in the local trajectory planner with optimization-based methods in the tube MPC and the controller. So if we would use a simpler controller, we would have to have a re-optimization or a smoothing procedure past the local trajectory planning. And by integrating that into the controller, we can skip this and focus on only having 2 software components. Looking at the software development workflow, so how did we approach that? So I think the first point here is really something which is probably a little bit different for our team than for other teams or for other approaches. We said from the very beginning, we are targeting a 5 to 6 car race. And for this race, we are developing all the components, and then we are bringing them together and we are testing them also in the easy scenarios. We're testing them from the very beginning, all the software in. So we're not bypassing components. We're not like spoofing signals and whatever. So from the very beginning, there was always the full software stack running. And that gave us, in the end, I think, a competitive advantage because we weren't bothered so much with integration issues as we brought in new functionality. We just have to activate a flag and then we could go. So for example, or another thing, we have been running with full obstacle avoidance basically from day 2 at testing. So even if there wouldn't be any other cars on track, we have been running with full obstacle avoidance because the car, as it doesn't see anything, it doesn't avoid anything. But having all those things already there, it gives you a lot of confidence that your startup procedures work, that your data logging works, and you do get the data of all those algorithms. And I think that was something which was probably one of the advantages we had, or one of our strengths. The second point here is we used a lot of continuous integration tests via classical CI/CD. Obviously, we can't like bring a unit test for every single software functionality, but running a couple of well-designed smoke tests to just like launch the software, let it run a couple of labs, put it into a few different scenarios, that's already giving you a pretty good sense of if something changed or if something changed to the worse. So that automation is taking away burden from the developers to test and to simulate, and that frees up more time to actually work on features. Another point in that is we used a semi-automated it has been like well for most of the for most scenarios, and then you can fine tune on the real race car. The very last point is also again it is focused in reducing our time from the first test at the track to actually having a final product, which is a fast race car. And how do you reduce simple simulation models? We often use simple models for the car in our software. So there are simple assumptions which the software uses about the car. But our simulations are built to actually reflect all the details of the car. So that's, for example, using nonlinear tire models, that's modeling suspension dynamics, that's modeling sensor noise. So sensor noise is something which is quite easy to add. And a good example is like we made a model of that space drive steering actuator, and just being able to replicate all those details. So that gave us a competitive advantage. So for example, also another thing here is we replicated actually all the CAN interfaces. So our simulator was using the exactly same software as on the car. That makes it so much easier to deploy software. If you change something like this, and for example, in the startup procedure, you can test it in the simulator, and you're really sure that when it works there, you can go to the racetrack, and then it's actually going to work. So we had a couple of situations where we had like 10, 12 developers working for 2-3 days between testing days, and we've been going to the next test day, and the car has been running from the very first run in the morning. So without any issue, just because we were able to simulate all those things. So no integration issues, and no, or a lot less issues from the transfer from simulation to reality. Looking at the tools, the middleware we have been using, so obviously all of this wouldn't have been possible with the strong backing of the open source community. So all our software was integrated in ROS2. We used medium modular approach. So in the end, you have been seeing the software architecture before. There has been running like 12 to 15 different ROS nodes. That's, for the complexity we had, is probably still a rather small size. The reason for that is that we had some challenges with actually getting the data flow running as performant as it should be. But that's something we are working on. So I think there's a lot of improvement. So we use Cyclone DDS, which is a DDS implementation, which is with ROS2 Galactic now the standard implementation. And with the latest version, it offers a lot of new features which can help us to bring those communication times down. So a good example here is is LiDAR point clouds. So if you have to transfer them from different ROS nodes, that's not so easy, and that takes some time. So we decided at some parts to actually bring functionality into the same ROS node and not send the data. But in the long term, we believe it's better to have multiple ROS nodes and to actually transfer that data using zero copy mechanisms, for example. We also leverage Docker and Docker Compose to orchestrate our software. So that containerization allowed us to actually make the deployment of the software on the car very easy. So how that works for us is that the software is built in the cloud, and there it is. It's like tagged, it's versioned, and then in the morning before the test, someone can download all the software on a hard drive, and you can upload the Docker containers. So you don't have to rebuild on the car. You don't have to check out commits of like 5 or 10 different Docker Git repositories. You just upload all the Docker containers, launch your software, and you're good to go. So that was a pretty good strategy, I believe. And coming towards the tools we used, or the programming languages we used. So we used a mix of basically 3 things, which is Python, which we mainly used in areas where we had machine learning based algorithms, because many libraries there are targeting Python, and there are a couple of open source implementations which you can build from. If it comes towards, let's say, compute intensive perception algorithms, we use C++ just for its raw speed. And the control algorithms have been developed in MATLAB, and then using code generation and a custom C++ wrapper for ROS2. That was basically the strategy we applied here. The reasoning why we made the custom wrapper is that we had to tune a few specific things to actually achieve the desired real-time performance, because for the controller it was really important to run at a certain frequency, so 100 hertz in this time, and that it actually meets all its real-time requirements together with the DDS implementation. And that has been a challenge, but we managed to get all of that running because of it's like ROS2 gives you a ton of tools there, and you just have to find the right ones for your task. So depending on either if you, for example, want to maximize for throughput or for latency, there are like different settings you can choose. And so that's why we were going for that custom implementation, so that we can fine tune the DDS and the ROS2 really specifically to our needs. I've been talking a lot about simulation. So how does that actually look like? So our simulation is based around a hardware in the loop simulation. So that hardware in the loop is the middle block of this. So the gray area here is our vehicle physics real-time simulation. So that's a dedicated computer built by Speedgoat, which delivers real-time performance for the vehicle physics. So that computer is optimized for giving you a very detailed physics simulation. And we run that in conjunction with a strong GPU server, which is running our what we call environment simulation. So that means the 3D rendering of the cars. That means the camera and the LiDAR simulation. And all of that is based on Unity. We have a couple of custom-made plugins there, but we're working right now to see where we can integrate that with SVL simulation and leverage even more tools what the open source community is offering. So those vehicle physics just need to be controlled by some autonomous driving computers. And what we made here is what we did is that we stacked up multiple of those. So we had, in fact, up to 8 separate autonomous driving computers. So we could run 8 cars at the same time with real time. So real time here doesn't only mean that we meet our real time specifications. It means that we can run those simulations at the same time as a lab needs. So if we run 300 kph, we drive a lab at IMS in 60 seconds. And that's really an advantage compared to other simulation tools where you simulate all of that, that you can run that simulation at the same speed as the actual car is running. And so for one of those cars, we had the capability to simulate LiDAR and cameras. For all the others, we used a virtual object list, which was published by the simulator and was then bypassing the perception algorithms. So the next couple of slides are going to give you a little bit more detail about what kind of algorithms we used. I don't have enough time to explain all of them. I'm not the expert on all of them, but if you have questions, just feel free to drop me a message on LinkedIn or an email, and I'm going to connect you with the people who are experts on that topic, or just give the explanations where I can. So our 2 main detection pipelines were the point RCNN for vehicle detection, and the second radar and the radars for long-range detections. We managed to achieve detection distances of around 70 to 80 meters with the LiDAR. That value is a little bit, let's say, difficult to give because it depends a lot on the spot on the track you are, the orientation of the cars and everything. But usually 70 to 80 meters have been a pretty good average of what we could do there. The radar is even more performant, so you can reach like 100, 120 meters with that reliably. So the radar gives you a chance to detect already that there already is a car. Also, if it doesn't give you a very precise estimate of where the car is. Both of those pipelines have been backed up by the camera pipeline, but as mentioned in the beginning, we didn't really get there to integrate that just due to time constraints. So the 4th pipeline was the LiDAR pipeline, which we have been running in addition to the machine learning based pipeline. Also, for example, for debris detections or detect things which are not cars. So basically, you can think of that as the point RCNN being a little bit overfitted to race cars, to really only detect race cars. And the clustering based approach should detect all of the objects which were there. The object tracking itself was a mix of a Kalman filter-based approach and a classical data association algorithm, the Hungarian algorithm. Actually, what we found out is that this data association has a really strong influence on the performance of the tracking. So getting that right is pretty crucial in achieving top performance. But yeah, also because that data association has a strong task in outlier rejection, and there's a trade-off you have to make between outlier rejection and reaction time. And yeah, that's a pretty hard part to get right. And that's something I think where there's still room for improvement. Coming towards prediction. Prediction was a little bit of a difficult thing to figure out what the best approach was. We tried a couple of different things. We tried purely data-based method. We tried purely rule-based methods. And in the end, what we found was probably the best performing approach is a mix of both. So use the classical physics-based approach for the very short-term prediction, and for the little longer-term prediction, either use something which is based from the left and the right track boundary and the race line, or use something which is trained on data. So we tested both of that and found strengths and weaknesses. Basically because it really depends. I think in the long run, the data-based approach is going to outperform the rule-based approach, but that also requires a lot of data. That's something we still have to improve upon. Coming to trajectory planning, I already mentioned that we were using a graph-based approach. So that approach was inspired by some of the algorithms developed during the DARPA challenge, and we extended it especially to go for more efficient search algorithms and to really fine-tune it towards the racing approach. So what we see here looks pretty complicated. I'm trying to break that down a little bit. On the bottom, you can see what we call the spatial nodes. So the nodes which are distributed along the racetrack. So the S coordinate is oriented along the racetrack. So it's basically the progress along the track. And the D coordinate is the lateral coordinate along the racetrack. So we place different nodes here, marked in black along that racetrack. And their connections are laid out here in gray, because all of that are pre-placed before we run. And that allows us to pre-compute a pretty good amount of the stuff which is needed for the online part, and therefore to save computational time. What you then see here in red and green are different velocity profiles, and they are generated based on a sampling-based strategy. So none of this is pre-computed, and all of this is determined during the runtime. And just to give you a really short insight in how that works is, first of all, we sample a variety of different profiles for the first stage. And then in the second stage, we again sample from those blue boxes which were highlighted. And then you can see that multiple profiles fall into the same blue box. And that allows us to sort out ways into that blue box which are not as performant as other ways. So we don't have to generate all of those velocity profiles which are possible, but we only continue with the most promising ones. And that's again a strategy to increase the efficiency of the search. So coming to that model predictive control, I mentioned that the local trajectory planning is more towards more focused on planning the course trajectory. So not giving all the details or not refining it up to a centimeter level. So that's the task of this tube model predictive controller, despite actually controlling the vehicle. So the green tube is what we call the driving tube. And this driving tube is generated in form of a target trajectory plus some form of optimization margin. So this driving tube is guaranteed to be collision-free, and the controller can re-optimize and refine its driving trajectory within this green area. You actually have to think of that more as a two-dimensional thing, but it's very hard to depict the time or the time domain of this. The red tube is what we call the uncertainty tube. So that's a prediction of where the car can end up. Usually in model predictive control, you only have a single prediction of what's going to happen. But in this case, we replace this with an uncertain prediction of all potential outcomes of the next 2 seconds. So this is important because there are always inaccuracies in the model you use. So the car will always deviate from the nominal prediction the model predictive controller is calculating. And this approach leads to a strategy where the car is actually exploiting all of the vehicle performance on a short-term basis, so on the very beginning. And the longer the prediction horizon is, the more cautious the car becomes. So it leaves a little bit more space to the left and to the right, because this uncertainty tube is actually growing with the prediction horizon. So in front of the car for the first 0.2, 0.3 seconds of the prediction horizon, that's very narrow. And at the end of the prediction horizon, which is 2 seconds, it's rather coarse and it's actually filling up the full driving tube. So the car is exploiting that in the sense that it's driving closer to the left or to the right limit of the tube, but it's staying cautious in the face of uncertainty. So for long-term predictions, it's cautious, and for short-term predictions, it's very aggressive. So that was a lot of technical details. I'm now going to explain the final competition format where the organizers and the teams settled upon. So what was done is not a true multi-car race, but it was important to everybody that we reflect the capabilities of what has been developed. So reflecting things like object detection, dynamic replanning. And given all of that, what was decided is that there are 2 stages of the competition. The first is the qualifying phase, which was a classical IndyCar qualifying. So what that means is that the car runs on 2 warm-up laps, so to bring some temperature in the tires, and then run 2 push laps. So the 2 push laps are something which are not really known to people who are more used to F1-like races. So they only have 1 lap, which is counted for the qualifying, but that's something which is pretty natural in IndyCar racing or at the Indy 500, that they actually run 2 laps. So, and then your time is measured based on the average of those 2 laps. On the cool down lap, there was an obstacle avoidance element, which was done by those 4 pilots, which you can see here on the picture on the right. So the car didn't know where those pilots are, and it had to replan its trajectory around that. And it wasn't allowed to obviously hit them, and it has to safely navigate them before coming back into the pits. The 3 teams which showed the fastest lap time during this challenge were granted a rerun of their push laps. So with a slight modification, and that's something which was one of the challenges in running at the speedway at the in Indianapolis in late October. It was very hard to get temperature in the tires and to actually get the car to build up temperature and so that it can perform the way it was designed. So what was modified for the final is that the teams were granted 4 warm-up laps and then 2 push laps. So slightly different format, but targeted to bring more temperature, and so that allowed teams to actually drive even faster during that competition final. I've got another video here with me, which was from the day before the race. So after this competition was announced or was laid out, obviously one thing most of the teams did is trying to find where the limit of the software is. And we brought one of our practice runs here. So as you have seen, also if you find the limit, sometimes things go wrong or you're slightly above the limit. But we believe that this, actually the fact that multiple teams had a spin out at that day shortly before the race showed that we actually achieved what those cars can do, and that the software has been capable of running the cars at a performance level which is actually in the area of what those cars can run from a vehicle dynamics point of view. And I think that has been something which is a really great achievement. And I think I can share here that the car wasn't hurt, so nothing bad happened. And that's also one of the strengths from racetracks. So you can try to find the limits without being afraid of that something happens. So obviously your car can get damaged, but that can all be repaired. That costs money, but there's no human in the car. There are no humans directly in the areas where that can happen, because those racetracks are certified to be run that way. So a racetrack is a great proving ground to actually push the car to the limit. Having said all of that, I think we have been pretty proud that we finally made it to the first place. It was a very close final with the two other European teams. I think both of them did a pretty great job. So Polymove did, I think, the fastest actual speed which has been run during that final, until an issue with their car stopped them from competing furthermore. Euro Racing has been running the single fastest lap, but the car slowed down a little bit for the second push lap, and that let us win the competition with the fastest 2-lap average in the final. And that 2-lap average was 135 miles, which is around 220 kph. And the top speed we achieved was around 250, 255 kph. So that's not the total maximum of what's possible. But given the circumstances from the temperatures, so being there in late October, I think what was demonstrated is, probably 85 to 90% of what those cars can do. So we are all pretty sure that given a little bit more time, it's actually possible to squeeze out a slightly faster lap time. All right. One thing I would like to point out here is that we are a strong believer in sharing what we did here. So not only nice PowerPoint slides, but from also from a code perspective. So I already have to say that not everything which was there on October 23rd is already up at GitHub, but we are working pretty hard to get it there. The key issue here right now is that also we have to add some documentation to make it usable for people who haven't been working with the team very closely, and to present it in a way which is easily understandable and that it can be integrated also in your software stack. There are some parts already there. So for example, the global trajectory optimization, a good portion of the controller is already up there, not the very latest version, but something which is close to. So just have a look at that GitHub page. We are working, as said already, with people in the community to actually bring more of our software stack open source, because we believe that's going to enable maybe other teams, but also other researchers to take those approaches, and they don't have to reinvent the wheel. So we have been relying pretty much on open source, and we want to give that back to the community. That has all been about the past. I think what remains is I can already share that this race wasn't the last race. We are going to go to Las Vegas Motor Speedway at January 7th. So the Indy Autonomous Challenge is going to continue. All 9 cars have been brought to Las Vegas already, and there will be a race which is an actual head-to-head race on in the program of the CES. So there's a ton of exciting things which are in front of us. And yeah, even though it didn't make it to a full multiple car race, we already worked on that, and I want to share a glimpse of how that could look like. So this video has been recorded during a joint test with the team from Modena Euro Racing. So yeah, just have a look of what can happen in Vegas, and we are pretty sure that this is going to be there. These cars have been running at speeds between 80 and 100 kph during that video here. So there haven't been any rules. The cars have been fully detecting and replanning around the other cars. So yeah, both cars have been fully autonomous here, no human interaction. And I think that's already a pretty good achievement. So I hope that we are probably going to meet some of you in person in Vegas. There will hopefully be again a nice live stream so that all of you can watch it. And the Las Vegas Motor Speedway is probably going to allow us to drive even a little bit faster than on the Indianapolis Motor Speedway. So thank you for your attention, and I think we have pretty good amount of time for questions. And yeah, all right, thank you.
Thank you very much, Alexander, for this awesome talk. And I think that's really a subject that all fascinates us all, and you showed what can be achieved with a great team, and giving back to the community, the open source. So I'm sure there's a couple of questions. We have. If you're on the Twitch stream, you can write your questions down in the chat, and I will just go through them. And later on, we can have some questions here from the people joining in the Google Meet. So let me start there in the chat. It's a question by Alex. What is the specific challenge which prevented you from using all of the sensors?
I think, to be pretty open here, the key challenge was time. So due to the pandemic, the cars wasn't it wasn't possible to get all the people into the US on time. It wasn't possible to get all the cars there on time. So we lost some testing and some track time, and due to that, it has been a pretty hard challenge to make all of that happen. Just to give you an impression, the car which you can see here was finalized in early September. There has been a ton of supply chain issues with just following up on all the impact the pandemic had on the companies, on the universities, and we had to navigate all of that. So there weren't really specific technical challenges. It was just a decision which had to be made due to resource constraints.
Okay, thank you. I hope that this audio sound of my mic does not transport to the Twitch stream, so and apologize for that. Next question. What method do we use for prediction? Is it learning based? I think you answered that.
We experimented a lot with, but it's probably worth to give a little bit more detail of what we tried there. So obviously I can't say what was used in the final race because it was static obstacles only, but we experimented with 3 different approaches during testing, and that was one purely data-driven approach. That was one approach which was purely based on classical physics, so constant turn rate, constant velocity model, for example. And there was one approach which was mixing that in the sense that we used a data-based approach, but we didn't let the neural network learn everything from scratch and let it combine different information from the physics-based prediction, the race line, and the track. All of those have specific pros and cons. Probably what I can share here is it's pretty hard to train a data-based approach because you have to have running cars before you can gather real training data, and you can't run cars before you have a prediction. So what we believe is the right approach to start with a rather simple approach, have the cars running slow or not as close to each other, collect the data, and then refine your algorithms. And that's what we're trying to do for the Las Vegas challenge.
Thank you very much. Next question. Do you simulate the tire temperatures in the simulation as well? Do you have a model inside there?
No, we don't. Maybe to give some of the reasoning here is, I think it's very, very hard to get that right, because it's hard to get data to calibrate your models. And so, yeah, again, that was one of the effects where we decided that we can't model it correctly, and we didn't want to deviate the simulator towards a state where it's giving you effects which are not there on the real cars. So, for example, we don't really have data on how much the tire is going to improve when it gets warmer. So that would have just been a guessing around, and then you could have overfitted to the simulation.
Thank you. Another question about the vehicle physics. Did you develop the vehicle physics simulator in-house? And an additional question, is it deterministic?
So the vehicle physics simulation is mostly self-developed. That's some know-how we bring from our institute. So like one of the institutes we work for is the Institute of Automotive Technology. So there is a ton of models there from previous research projects which we could base our code upon. But some of what we use is also based on like standard Simulink models. So there's this vehicle dynamics block set which can be used. So it really depends. So for some things we use standard blocks, but for some things we also have like custom built models, and then that's all orchestrated in a custom built way. The second thing, so I think it's hard to answer that question only related to the vehicle physics. The total hardware in the loop simulation is inherently non-deterministic because it's it's running on multiple machines which are not synchronized. But in this case it's actually intended because in reality you also can't synchronize the physics with your software. So I know, or there's some desire to synchronize those things, but I believe there's a value in doing both, so asynchronous simulation and synchronous simulation. We use synchronous simulation a lot during controller development, where all things are just simulated within a single Simulink model, and that's obviously deterministic.
Okay, thank you. Next question. What algorithm was used for LiDAR-based localization? I think you showed us one slide where you get a glimpse, but maybe you can give us some more background on that.
We also experimented with two different things here. What we ended up with is, as said, was more like a sanity checking thing, where we used distance to the wall or distance to the track bounds to verify that our localization is okay. Obviously, for Vegas, we're trying to improve on that, and that should look towards a point cloud-based localization with the scan matching. But one of the challenges here again is that there are no like on-site data sets. So acquiring all of that takes time, and then you have to refine your algorithms, you have to refine your models, and you actually have to test all of that, and your testing time is pretty limited. And that's where we're going to balance different needs from different software modules.
Okay, thank you. There's a question about ROS. You mentioned having to combine some of the ROS nodes to improve data transfer efficiency. Can you explain where that was necessary and why?
Yeah, so I think one of the challenges we had is that some of the stuff we used was in Python and some of the stuff we used was in C++, and you can't leverage all the, let's say, strengths of ROS and DDS if you run part of your software in Python. So yeah, that was one of the challenges we had to like minimize latency and minimize the actual time, how long it takes that the data flows through the total software stack. So you always want to minimize the end-to-end reaction time. And for some modules, we found that it was more efficient to actually let them run in a single process, especially for modules which don't have a lot of computational load. But yeah, I think there is some room for improvement, especially if you have all of that running in C++, because there are some tools you can leverage, for example, like zero copy, to reduce that time and to let the data flow run more efficiently.
Okay, thank you. Another question: how did you collect data for the point RCNN? It seems data collection was a challenge in general. Was it using simulated data or real world?
Both. So we we generated a lot of data in simulation, which is quite nice because you can also generate your labels from simulation. And that was then enriched by data which we gathered on the real racetrack. So again, here we had the advantage that we had that clustering-based approach and the point RCNN-based approach. So we could start running directly from the clustering-based approach. And also the point RCNN trained on simulated data was already giving a performance which was reasonable. Obviously, it wasn't super perfect. So but that combination of those two different algorithms allowed us to run pretty fast with other cars to actually collect the data without doing things like specific data collection runs. Maybe to say that here, one of the challenges with the simulated data was that it was showing too many reflection points because it wasn't really taking into account all the details of the LiDAR reflectivity physics. And there we were ending up with too many points per car. And that was something which the neural network had to learn from the real data.
Okay, thank you. I think please continue asking questions in the chat. Meanwhile, I would like to introduce another guest here in the call. That's Joe Speed from AD-Link. He just joined us here. Hello, and I think you both met there in Indianapolis. Great to have you here on the call, Joe, together with Nicholas, Dave, and Alex and Alexander. So maybe you guys, sure you have some questions. Just open your mic and ask them.
Yeah, very good. I'll just say, so I've been working with Alex for over a year now on this Indy Autonomous Challenge. He's done something incredibly important, which was he led the Indy Autonomous Challenge Base Vehicle Software Work Group. I think IAC had this original idea that they would just build physical cars, give them to universities, and then wish them good luck. And, Alex, myself, Gina, many others realized that was not going to be a recipe for success. So Alex led the development of a base vehicle reference implementation so that the universities would just get software that they could use to go do a yellow flag lap, and then it's up to them to take it racing, make it go faster. So that was
just adding on what Joe just shared. So I think that was one of the success stories of collaboration during the event. So so to give you a little bit more of background, that base software covered, for example, all the sensor drivers. So some teams took the lead on working with the cameras, some teams took the lead on working with radars, on working with LiDARs, and we tried to facilitate a community where all of those results and insights were actually shared with the other teams, because that was something we considered like the non-competitive part. And coming up with that challenge of not having enough cars, there was actually that addition that the cars were, that we built this reference implementation to run slow laps, so slow is relative in the sense that that was 60-mile laps on Lucas Oil. And I think what we can say is 60 miles is similar to 100 miles at IMS. So as said, it's already faster than you can drive in the US on the interstate, right?
Yes. Yeah, Lucas is it's a small track. It's not like IMS.
Yeah.
Definitely so. The and Alex, some things you mentioned about, I think your team would be happy to know that there is now a new rather nice rather elegant Python API for the Cyclone DDS. So you can work with that directly. So there's an engineer from CERN. He's like a CERN PhD guy at ADLink who worked on that. Also, you know, you've got the ICERIX built in for Cyclone in the Galactic that you're using. And one of the things that does for the teams is every message from 16 byte to, you know, 16 byte struct or a 4 megabyte camera image or point cloud, it makes it a very small fixed CPU cost. So the CPU cost is the same regardless of message size. So I think that'll be quite good for you. The thing about the tires,
Yeah.
you know, it's frustrating that the IAC is held in late October. Like if it was at the same time as the Indy 500, which is late May, hot, dry, sunny, I think these cars would have gone 20 or 30 miles an hour faster. It's you know, the stickiness of the tire, it's a function of temperature. And you had this huge rain the day before the event that washed all the rubber off the track. So, you know, you've got the cold temperatures. You got this issue that the tires are designed that they don't even begin to warm up until 120 mile per hour. So your warm-up laps have to be 120 mile per hour for you to start gaining that 5C per lap. So it's tough. It makes it challenging. And one thing I wanted to ask you is, you know, Vegas, like everyone thinks of Vegas as this hot, sunny place. Well, they're half right. Like it's sunny, but in January, you know, it's like, you know, it's 38 to 59 degrees Fahrenheit. You know, do you need tire warmers? Like, what can we do to make this better for you in Vegas in January?
Yeah, I still have difficulties with converting 59 degrees Fahrenheit to Celsius, but I did the research here as well, and my feeling is Vegas in January won't be much different from Indy in mid October, probably 1 or 2 degrees something, but it won't be like considerably different. And I think there are two ways here where at least we are going to push for. The first is obviously, I think we only started getting into that direction like 2 days prior to the race. So that's something where teams now are building an understanding. I think there have been some like rumors about how tires work and whatever around, but if you work with race cars for a longer time, you somehow realize that each tire, each manufacturer, each chassis is different. So there are a couple of learnings which we can take from October. As you said, like I think a couple of teams were surprised by the fact that you actually have to run 100, 120 miles to actually bring temperature in the tires. So these things is something I think we as the teams already learned, or there's some learning on our side. And the other thing, I personally don't think tire warmers are really, let's say, best strategy. I would actually prefer to keep a strategy which is more towards let's say multiple warm-up laps thing and work on the race car setup. And here's the reasoning why. I can tell you that at the days where we had sun, the tires were warm when they were sitting in the sun, and then they started to cool down if you drive too slow on the track already on your out lap. So warming the tires is so still then it's like necessary to go out fast and to get all of that right. And my feeling is that it might be more sustainable for us to like better understand of how that works and add more warm-up laps, just because that tire warmer thing it just makes it harder to get it right, in the sense that it probably adds a few percent of top performance, but to achieve a medium to medium good performance, it probably makes it harder, because you could rely too much on the tire warmers. You can get overconfident. So that's my feeling. And also, I think what can be shared here is the setup of those cars has been changed after that spin out we and that other team had on Thursday. So I think we're also understanding now how, or better, or increasing our understanding of how those cars work. So, for example, just to share that, obviously at lower temperatures you need more downforce, and if you have more downforce, you get more temperature into the tires. You can drive faster with cold tires, which is again making it easier to warm up the tires. And I think if we probably have one or two more iterations on the race car setup, we're going to end up in a situation where we're pretty well positioned for Vegas to go definitely those 20 miles faster, as you said.
Oh, that's amazing. I didn't realize that. So it makes total sense. So you can really get it dialed in. You know, more downforce, of course, is good. And if you're not driving it, yeah, okay.
So you're basically trading like a few miles per hour top speed against more downforce, and then but that enables you to reach that higher speed again. So
I think that's, given the circumstance, I think that's a worthwhile trade. You know, honestly, it's we still don't know what the actual potential top speed of these are. You know, they're built to do something like 180, 185, but we've not driven it, so we don't actually know. But certainly, you know, we're not at that kind of realm yet. But it would be amazing. You know, we're going to have a whole month to get these things dialed in for Vegas. One of the other things for Vegas is, you know, at IMS, there were some controls around capturing the data, sharing the data. At Vegas, the brilliant thing about Vegas is it's Vegas. You can do anything. Okay, so you can do all the LiDAR mapping. You can do all the camera, and you can put it all on the internet and just let not just teams, but everyone in the world have access and iterate and work on the problem. So is that something we can try to figure out how to exploit and work together on?
Yeah, I totally believe so. I think you guys already took a little bit of the lead on working with the LGSVL simulator, bringing a map there with for Vegas and everything. I think Vegas is going to be really an enabler for the long-term thing of this challenge. So, given the short time frame until January, I think really what we should do is, or I think what I'm pretty sure what we're going to do again is to start that sharing between the teams, and also having the opportunity to get in the experts from the community or from certain companies is going to improve our speed. To be honest, my feeling actually is that one of the most challenging thing will again be to get, say, everything around the track right, to get the infrastructure set up, to get the race cars set up actually. So as far as I know, IndyCar or the Indy Lights are not driving in Vegas. So for IMS, there are pretty well-known, like, let's say setup sheets, like Juncos Racing could rely on. But in Vegas, you have 20-ish degrees of banking. And I don't, so Vegas is actually, like, everyone is saying like Vegas is going to be a faster track and it will be great and easy, but Vegas is having some very specific challenges with that high banking. One of the stretches is not really a straight stretch. It's more form of an egg, and that's bringing some, let's say, challenges which have been not on top of our mind to us.
Yeah, it is a fun track. It's a nice track. So I was out there a while back. Jeff Bezos threw a party, and so I got to go do hot laps on the track with a professional race car driver. It's nice. Like I think it's going to be a lot of fun.
For sure. But yeah, so think right now everyone is focused in getting all those details right. And yeah, but I'm pretty optimistic. We have a ton of test days there. So
Alexander, specific, Joe, specific to that point, is there a point cloud available already, or that will be publicly available? Or is somebody still recording it, or what is the date for the recording?
Yeah, I think so. So the first tests are going to be in early December. So I'm hopeful that we have all of that by early December. And yeah, but right now, yeah, the cars have just arrived there. Many of the international teams are traveling next week or something. So I'm personally expecting Vegas to gain a lot of traction starting after December 1st. Because then everybody is in Vegas, and yeah, they're going to do a few tests already, I think, in late November. But from the experience we have, these are probably more shakedown runs to make sure everything works correctly. Because also during those data collections runs, you really have to make sure that it's collected right. That's
Yeah, so Keist is going to go do some laps and record everything here into November, I think is what's planned. I hope they've moved to Galactic. Otherwise, I'm concerned that, as you know, Rosbag 2 is quite broken and foxy and is not capable of logging all the sensors. And so they need to get that onto Galactic. I'm also in discussion, hopefully it comes about, with Seagate. They make the world's fastest NVMe SSD, and I'm trying to get those into the cars before Vegas as well.
Yeah. So there are a couple of challenges. I think what you can really say is that collecting that amount of data isn't easy. As Joe said, that's like an ongoing thing, and where I think Apex and a few others have made significant contributions to Galactic, which really improved the state of the art, or the state of Rosbag. But especially if you look at cameras, it's still, I think, probably challenging, because for cameras, I think it was less a Rosbag thing, but more a hard drive speed thing. Or
I think the combination of so we've enabled the zero copy, although I guess in the current iteration the integration into ROS is fewer copies, but it's still quite good. So we've got to get that strung together end to end, right? So we've got to add support to camera drivers. The middleware supports it, but the rest of ROS does not yet. And so that's what we need to work on. The Rosbag improvements are good. The hardware that's in the car is good. If we can get these Seagate drives in, it becomes even better. And so the pieces are coming together. It's not all done, but it's nothing but hours. Like we all know what has to be done.
But I think what Joe just mentioned is also one of the challenges we had in terms of making that latency reduction. The middleware can do it, but Galactic was released like in May, and like some of like the decisions around of that had to be made before that, and then you had so what I think what's really a learning for us is like, as Joe said, you have to like design that thing from end to end. The ROS nodes have to do that. The Docker has to do that. The hard drive has to do that. And what limits your speed or your latency is always the weakest part in the chain. So I think we now have the foundation to build that system which can do that. But we now have to like understand of how to build the software around to fully leverage the potential which is there in the middleware. Also, maybe that might require some changes to drivers. And what we found is, or what I believe will be a challenge to the open source community, is that if you want to max out those things, you're usually like narrowing down the use cases, or sometimes it's harder to access or it's harder to use if you like really like max out the last 2-3% of the performance, because you sometimes have to make design choices which, for example, like decrease reusability, or like decrease the general applicability of certain modules. So that's a very hard thing to balance from time to time if you really want to max out the last 5 to 10% of the performance.
Yeah, but some of these things we're talking about, like taking advantage of the loan message API, the Icerox zero copy, all the work that Apex AI, 80Link, and other contributors have been doing on the Galactic ROS middleware, which is a project of Eclipse Foundation. So there's a lot happening in Eclipse. You've got, Bosch and all these automotive people in Eclipse Foundation working on these things. It's not a few percent improvement, right? It's actually like, order of magnitude or more improvement. Like it's rather dramatic. So the gains are there to be had. We just have to do the work with, ROS, with the camera drivers, perception, all of these things. But the improvements are there to be had.
Yeah, and but just sharing that, I think that's also an educational point. So what I can share from a university perspective is like autonomous driving is probably one of the challenges where you have to bring the most different technical fields to the same table. So getting the people who or building a team for people which are where you have experts in vehicle dynamics, where you have experts in math and optimization, where you have experts in perception, where you have experts in software design, and you have experts in actually leveraging all those, let's say, details of your middleware. So I think that's something where we believe that these projects which we're doing here are helping to actually educate the students. And so as I think I shared that already in the very beginning, it's like TUM isn't only 15 PhDs, it's like 45 undergraduate, graduate students. And that's something we really believe is a chance to bring to all of them. And so this project is so much more than only doing the research on that, because it's like really like educating the next generation of young software engineers with all those different backgrounds.
The open source community,
maybe let me throw in another question from the chat, because I think that fits well. I think it's Steve Lemke asking about the camera. I heard one challenge last time was setting the camera capture parameters to prefer higher frame rate over lower resolution. So what is your expectation, Alexander, about getting on the camera node?
To be honest, probably I am personally not the best person to ask that, for two reasons. The first is we prioritize LiDAR and radar over cameras, so we haven't been playing around a lot with the cameras. And the second thing is that I wasn't playing around with the cameras, so I can't really share any details on that just because I don't know that. From what I heard or from what I knew from our base software activities, is that one challenge was also to run them in Docker containers. I don't really know what exactly the technical reason was there. That was a challenge to bring them into the Docker container. And I don't really know about the settings challenges.
It's solvable. There are some hiccups and challenges when you start Dockerizing the things. It is solvable. You do incur a nominal hit, but not severe when set up correctly. But it's not well-traveled ground for everyone yet. So, yeah.
Actually, a quick question. Go ahead, Alex.
Yeah, I have kind of a question for everybody, but I'd love to really hear your thoughts on it, Alex and Joe, is autonomous racing. So there's Formula E that's now out there, right? And that's supposed to kind of drive the industry. I mean, it all kind of starts with Formula One, right? Then they brought in Formula E because Audi and Porsche and companies started pulling out of racing, because we all know racing is super expensive. And it's hard for companies to find value in that. So, I think ABS came out of Formula One. I believe even rear view mirrors came out of there. There's a lot, traction control came out of racing. But now as things change in the world and as vehicles change, it's harder and harder for companies to find value to spend millions of dollars to go racing. Do you think that autonomous racing is the future? And the reason I kind of ask is because, you know, in racing today, I'm a racing fan myself. I can relate to drivers. You know, I can say, oh, Kimi Räikkönen, he's a funny guy. But now, does Kimi Räikkönen get replaced with a TUM car? Or how do you guys see the future of autonomous racing unfolding? And especially when it comes to the expenses and for car company or any company really to legitimize that type of investment?
Yeah, I think I can probably start on that one. So that was basically, I think, two things. So the first is how do you engage the public? So how do you make it something which is fun to watch and people like to watch it? So being in this thing here now for 4 years, working with Bareiß, working with the Indy Challenge, I think what we have to do is we have to still have that connection to the humans which are working on that, but it's not the driver anymore. It's probably be the, I don't know, the principal engineer of the team or whatever where you relate to. And it's obviously losing a little bit of that element of risk, but at the same time you can probably like stretch the technology to even harder things. So just, you know, obviously it's really risky to sit in a car when it runs 300 kph, but what if we could run those cars at 500? Then no one who's sane is going to say we can make a commercial event out of that where people run with 500 kph on the speedway because we're going to have fatalities or whatever. But if we're going to bring those autonomous cars there and tell the story the right way, in the sense that I think we have to tell the process or have to tell the story. And then there's a lot of things to relate there. I think the Indy Challenge did a good job with those pit lane interviews and everything. But I think we still have to figure out what's the right format. So, for example, maybe teams have to share more about their strategies and whatever. Yeah, I think there's potential there to get there. And to the other questions, to actually spending the money or the technology or the technological innovations, I think autonomous driving is at a different stage than classical car development. We are probably at a stage where they were at, I don't know, 1940 or something, compared to where we are now. I don't know, Joe. You can throw in a different number if you want to.
The speeds that you all were doing would have qualified you for the pole position back in like 1950.
Yeah, so yeah, so that's somehow my feeling. So we're probably in the 1950s of autonomous driving. So my feeling is there's still a lot of innovation which can come out of that without investing that much money. And I think just looking back in what this challenge brought, I think, yeah, Joe, the other sponsors, and all of us, we have been pushing each other to really achieve a new level of performance. So we increased and tuned a lot of things, and I think we all take back a lot of learnings which wouldn't have been there without this challenge, and that can lead to innovation, or not only that can, that is going to lead to innovation. And I think what is important now is so we have to find a way how to do this sustainably, in the sense that, so if we want to get innovation out of this, we have to like make this a multi-year thing or a 3 events a year thing or whatever. And we have to understand how that funding can come together, because like that's where you really fuel innovation, where people have the time and the freedom to actually work on those projects and get creative. But that requires, yeah, as said, a big team, and probably at some point it's going to be the team which is the most costly thing. So similar to as an F1. So just paying all those engineers is a huge challenge, and probably Vegas can be the next step in getting there. But we really have to engage the public and some big sponsors who want to be a long-term thing. We can't go collecting money from race to race if we really want to innovate here. We really have to find the strategic partners who want to work with the teams and want to learn and want to apply their technology and understand where it can be improved, I think then we can see those innovations. That was a long answer.
It's brilliant.
Some more questions from you here?
Hello?
Anna?
Go on.
You know, this IAC program, the estimates from state of Indiana is, you know, if you look at the state of Indiana, IMS, the sponsors, you know, 80 Link and all the others, and all the other people who contribute to this, and the universities, you know, we're probably somewhere around $120 million into this program. And just to give you some context, you know, in F1, that's like coffee money service. That's nothing, right? Like somebody like Volkswagen or Daimler
Haas runs on about
that.
80 million a year. Haas, I think they're the least funded team. And then there was, you know, there's like a whole documentary. Actually, maybe someone is doing a documentary on this autonomous challenge already, similar to F1. I'm guessing that's probably somewhere behind the scenes, but Haas is like operating around 100 million, while Ferrari is closer to $1 billion.
Exactly. And you know, somebody like a Volkswagen.
We had 9 teams, and the series based on the number Joe just shared here.
Exactly, and and that includes designing and building a new car for all of them. So really, it's kind of a bargain, right? And you look at like the whole open source community rallied to invest and contribute and help support this, but it's already recouped. Like there are now improvements in the whole open source stack that make for better surgical robots, safer autonomous forklifts, better operating Roomba vacuum cleaners, right? Like it's so it's returning very fast, right? Like there are already improvements in the whole open source stack, the Eclipse Foundation, AutoAir Foundation, Open Robotics, because of the work of these teams. And so I see that this is, for me, it's a no-brainer, right? This is a really good investment for me, for my company, for industry. And there's, you know, brilliant things we can do of taking all this work and putting it in simulation on the cloud to have all of the other universities in the world be able to take the work that Alex and his team have done and learn from it and run it in simulation and do virtual sim racing with an eye to, you know, think about opening this up to where all the universities in the world can compete in simulation on the cloud to win a real physical IAC race car and join the in real life racing series.
So, Alex, let me ask you also, and to that point regarding access and whatnot, it seems to me that a lot of the tech involved here would also translate to a smaller scale chassis, you know, but at the same time, you know, if you're going to use real automotive components and have a CAN bus and a full-size LiDAR, et cetera, there are limitations there. But let's say something that conceivably could fit in the trunk of your car, so that, you know, the barrier to entry of cost for the chassis of something that still could run quite fast, you know, 100, 120 miles per hour for sure, whatever. But that if you wanted to go that route, as opposed to say even off-road, for example, which I'd be interested in your opinion on off-road autonomous racing at 1.2. But so do you feel this stuff scales? In other words, we've been playing around with like 1/5 scale chassis now and finding it's actually quite usable. And obviously you can put it in the car, transport it, the costs are not as high, but the software in certain aspects is spot on. What are your thoughts on scale, community?
So I've been working with a 1/5 scale car during my master thesis. That's now already 5 years ago, but so actually I was surprised, or when looking back, I think there's a lot we can take from there. So those cars are actually like so you can't, or you still have to invest into like a good chassis. Like you can't really take the super cheap ones and whatever. So I think, but you guys know that obviously better than me. But my feeling was that you can get off with spending a low 4-digit amount to get something which is pretty close, or like an 80% replication if you want to do algorithm development. Actually, sometimes it was harder to run the small cars because like they have like, if you have like an uncertainty in your model, they're just like bigger at that small scale, because like a 1 degree offset on your steering wheel, or for example, might be much worse than on your, like just like an example. But so that was sometimes even more challenging to get it run on that car, because it's just like, it's lighter, smaller, it's more agile. Actually, looking back, or also looking at the work Johannes Bates and some of the others are doing with that F1 to 10th, like Mado Bale, and for example, I think one of the challenges when we were always looking at bringing our software stack to those cars is actually compute. You have to use different algorithms because you don't have the same compute power. You could run the same algorithms and use it as a one-to-one test bed, but you don't have the same compute, because you just don't, like, physically don't get it in there because it's too big. Like, and I'm not talking about 10 computers, but I'm talking about one really good computer. So that was probably like the biggest challenge when you want to like.
And I was just going to say that's Joe, excuse me, but that's an interesting thing also within the AutoWare Foundation that Joe mentioned a moment ago. You know, there's an initiative now looking at what could the minimum viable on-ramp be for AutoWare, which is, you know, is first cousin to, I think, a lot of the things that you were using. And it's being determined, you know, almost as we speak. You know, is it a Jetson Nano, or is it an NX, or does it have to be an AGX or an AGX Orin or whatever? But it's coming. You know, that 4-digit kind of mark that you referred to with hardware and stuff, where you can really start to test some big boy algorithms. I think it's crystallizing in the next, you know, quarter or so.
Joe, you want to go ahead?
It is getting better with, you know, we've got more and more powerful small compute, right? As you mentioned. So AutoWare invested in renovating F1 10th to support Xavier NX. And then you've got Orin coming and things like that. So, you know, these 1/10 scale, they get people into it with physical cars for thousands of dollars. You can get into simulation for basically free, right? Well, not literally, but approximately. And then you've got these other classes. You've got the SAE Formula Student Driverless. You've got the EV Grand Prix. I'm really fond of the EV Grand Prix, and I see the work that University of Hawaii, Purdue, UC San Diego are doing on that. My problem with the SAE Formula Student Driverless is you spend so much time building the car that you now have no years left to teach it to be autonomous and race. And EV Grand Prix, what's that?
They love building the cars. I know all of those people.
I know.
I've been organized. That's you just can't take that away from them.
For me, it's my own prejudice. I'm more interested in how do you make it autonomous. And EV Grand Prix, I think it sidesteps that whole process by there's an off-the-shelf EV cart, race cart that you buy for like $4,000 or $5,000, and then you bolt all the autonomy onto it and you let it go, and it goes, you know, 60, 65 miles an hour, right? And it can carry, you know, it can carry 100 kilo of payload, not a kilo of payload.
Yeah, but so, or maybe looking, as I think one of the challenges is understanding of how those stacks can scale. Like for some things, or like only because your car is 1/10 scale, your algorithms don't need 1/10 scale compute. And that's, I think, sometimes the challenge. For some algorithm, that's probably true. For some, it's not. But also like with those NVIDIA platforms, they're ARM based, and so there are a couple of challenges involved. But I think if we look at what has been announced recently, also like I think those technologies are coming closer to each other, like the ARM technology, the workstation technology, but there are right now still a couple of challenges included. So I think what we would really love, and what we tried multiple times, to just bring that software stack on those small cars, but it obviously isn't as easy as one could think. But
Yeah.
it's just like it starts with all the dependencies and everything, and yeah, it's harder than you think.
So ARM, Apex AI, AD-Link, AWS, Tier 4, all of them are working to bring the stack from the IEC race cars onto ARM64, specifically the Ampere Ultra architecture.
Yep.
So that gets you from 32 to 128 core CPU. In 128 core flavor, it's 6 times more powerful than the Intel embedded Xeon that's currently in the race car. And so I think, so you think about, you could start with a $59 Nano and go all the way up to 128 core CPU with multiple NVIDIA GPUs, okay? And you can have that same stack and binary compatibility all the way across.
Yeah, but so maybe just adding one point here, I think we're doing, or the challenge here is that the software, like what you just described with, let's say, this tremendous amount of cores, is or does require some change in the way how we design the software. We have to design it more in the sense of a microservice architecture, small components which are easily scaled between like multiple cores. So I can tell you that so we've been utilizing the full CPU of that car. So it has been, I think it has been 8 physical cores, 16 hyper-threading cores. But we would have difficulties if it would have been like 32 cores with 4 times less compute, because some of our algorithms aren't easily transferred from a single core implementation to a multi-core implementation. So that's a challenge, I think, where software has also to understand, or we have to, just like this parallelization is something which is not yet solved, or where I feel there needs work to be done.
Yeah, there is work to be done, and the work is being done. So, and it helps that ROS2 itself is architected to be distributed. So whether you're distributing that across multiple cores or multiple computers, it's inherently supported in the architecture. So there is work to be done, but all the architectural underpinnings to accomplish that are in place.
Yeah, but someone still has to multi-thread our planning algorithm.
Agreed.
Yeah.
Agreed.
But I totally see that. I think that was also why we moved to ROS2, because we think that ROS2 is like giving you all of that flexibility in actually deploying that software compared to other tools. So yeah, I think the middleware, the architecture is there, and now we really have to gain traction on the software side and to understand how to leverage that. And that's probably what I meant with like, we have to understand how that software scales.
Sure.
In the sense that that software has to be designed inherently to have the scalability potential.
Mm-hmm.
And that, by the way, Alexander, again, is where I see, if you have, right now, it's a wonderful thing. It's just, it was awesome. It was a wonderful experience. It's just, and your presentation, by the way, was absolutely fantastic. I mean, good level of detail, good high level, really moving and stuff too, really outstanding. But if you want to get more innovation, especially on the software side, and you make it more accessible, again, with slightly smaller chassis and stuff, then you have the developer community engaging as well, as not just, the students when they're in school and so on. So, hence grows the ecosystem, but it is just wonderful to see. Hey, by the way, thoughts on off-road racing? And then Reiner, I don't know, maybe you should get to some of the Twitch questions, but real quick, off-road?
Doable, but a ton of challenges which no one has ever thought about. So let's frame it that way. I would be pretty confident that we can see nice, really multi-car autonomous races in the not too distant future. So let's say a couple of years. So really seeing 6 to 8 cars out there, and then we can probably take on off-road. So yeah.
Have you seen the latest progress from Cruise? They just released
Oh,
last week that they are now driving on the streets of San Francisco.
Yeah.
Do you think
That's
it's
pretty
real?
awesome.
Or is it
Hard
like
to
a
judge.
specified path that, they made it basically geofenced it?
I think they are definitely geofencing it, but the question is how big that area is, and that's very hard to judge. So if their geofence is full San Francisco, that's pretty awesome. If their geofence is 3 streets, that's probably more a marketing thing. But yeah, I think from what we've seen from them, they have a really good level of technology, and they're, I think, on a pretty good way in achieving that. So yeah, so from my side, I think they did a pretty good job, and
Yeah,
think,
Kyle and the team have
it's-
been doing it for a long time.
yeah. So I would say it's properly geofence, but not to an extent where you would say, okay, it's like faked or whatever. It's probably like, they have to, ensure that they don't have accidents and don't put anyone in danger. So it totally makes sense to do small steps. So probably, let's say, what will be the interesting metric? How fast they add more area in the sense, and I think that's where we're going to see their status quo, because like right now it makes sense to geofence it just to reduce the risk, but if they're adding that fast, that's definitely an indication that their technology is pretty ready to scale up.
Yeah, and even geofenced, I think a different question is it a controlled area? Yes or no? And the answer is no, right? They're mixing with random traffic. So that is impressive.
Yeah.
So Alexander, I'm looking a bit on the clock, so not to take too much of your time. So if we had something towards ending at 8 p.m., would that be okay?
Yeah, 8 is fine.
Yeah, so we may have 1 or 2 more questions.
Maybe Alex, Reiner, if you don't mind, one question was, is there any chance we could make the slides available or no?
I'm going to check. I think it should be possible.
Okay. Cool, thank you.
A bit of a segue question, but just more general. Obviously, you have a super awesome, highly functional team, and the sum is greater, or the whole is greater than the sum of the parts. And so, just wondering, like, I'm just thinking about team building and how did the team come together? And I think like building it and developing it and sustaining it is super key. And I think part of it is you're doing such an awesome job with making it open source and documenting it. And so just curious on what your thoughts are on putting a great team together and continuing it for years.
Yeah, I think probably the most important thing is that we're always trying to align the goals of all our individual team members, the goals of the team. So we're pretty much deciding our priorities and our focus all together, and that allows everyone to bring his piece to the table. And what we found is that when we manage to align the research projects and research interests of all of the individual team members, that's really going to fuel the team as a whole, because that's really motivating everyone. And if everyone can say, okay, I know I work on the part of this car which I have the most passion for, that's probably your target. You don't always achieve that, and there are always spots in that software stack someone has to work on.
Yeah, it was neat. You had Sebastian and Florian just living and breathing middleware and some of the other bits. They got to focus on what drives them.
Yeah, I think that's probably the big thing. And also, if sometimes people have to take on jobs or work packages they don't really thrive for, I think it's important I think that's a goal you have to achieve in the long run, in the sense that that's a value which should be key to your team.
So maybe Alexander, as you're originating from Munich, I think there's a name to be mentioned here, Professor Ernst Dickmanns, who did autonomous driving in Neubiberg at the University of the Armed Forces, I think back in the 80s. and drove along the highway for quite a while. And I recently learned that he was giving the idea to the DARPA of having some of these grand challenges to solve the problem. And so taking that and looking back what has happened from 2006, 2007, remembering Sebastian Schun is now working in a startup doing flying cars. So if you take your imagination out to the wild, what could or what would you imagine in 10 to 15 or 20 years? What can originate from what has happened in Indianapolis?
That's a tough question, right? So really what I think what could be possible is like, so I haven't been there in 2007, but I've been in Indianapolis, and I think that spirit of collaboration is something I would personally love to see to like continue and get more traction, just in the sense that like if we look back for the past years, I think we all have seen that solving this problem with a single company, with a single group is probably, I wouldn't say impossible, but for sure pretty expensive. So and I think there's something which we saw with other projects like Linux, which actually managed to like transform the world of technology with open and free software. And if we could see this to come out of this project here, I think that would be a pretty huge achievement. So, and my feeling is from like talking to a variety of people over the last months and years, that people are actually more open towards that. So the industry is transforming to understanding that there is a need for, let's say, in the first step, open standards, and then the second step is collaboration on the what they always call non-differentiating parts. That's pretty much what we did here in the Indy Autonomous Challenge. And if we manage to keep that spirit up and actually, let's say, bring it to a much higher level than a student-made project or a student-led project, I think that would be a great achievement out of this challenge.
And it is coming together. Like, you know, for myself, I'm old enough that I remember when every computer manufacturer had their own operating system. And eventually we all realized that's dumb, and we banded together and all contributed to Linux. If you look at the automotive environment today, it's kind of like the computer industry 20, 30 years ago, right? Where each automaker, each OEM, each tier one has its own software team developing code in isolation, in silos, to what is like 98% identical functional requirement, okay? But you're seeing that starting to break down and some convergence. So you've got the things that ARM is leading with the whole SOFI program, the Scalable Open Architecture for Embedded Edge, with a reference autonomy stack, which is actually very much the same stack that is the basis of your race car, okay? And you've got all of these companies and open source foundations. It's the Open Robotics ROS 2 with AutoWare, Drive-by-Wire, with Eclipse Foundation, middlewares, and all of that going into SOFI. And we've been shipping the hardware for that to automakers since August. So it's happening. And if we can bring this whole racing program onto into this environment, and if we can help to see all of the companies that are already investing and stakeholders in this to see how the racing will accelerate their own programs, I think that's the key. So you've got Toyota, Volkswagen, Conti, and many others, Electrobit, like all of these companies working together on this environment, this open source stack. It's all this like taking the cloud containerization, the mixed criticality, the security, deployment, OTA, all of this. And if we get them to all see that actually investing in the Indy Autonomous Challenge and these autonomous racing programs helps accelerate their own programs, then I think this all gets to where we want it to be very fast.
Okay.
Joe, I just have a quick question on that. If a developer team or a community team were to somehow miraculously raise the money for a vehicle and demonstrate, let's say at some track, that the vehicle performs capably or has the same vehicle, is there anything against community developers if they have the same Dallara vehicle participating in the future?
Well, the Indy Autonomous Challenge is university-based, but you can work with and contribute to a university effort. So go find some university friends. And I think, once we get all the simulation challenge onto cloud, that's where it really democratizes it, where, anyone in the world can find a way to participate and contribute. Our intent, our hope is, call it an ambition, not a commitment. But, if we can get this rolling with the right sponsors and get it all set up in the cloud, you should expect something like whichever university can win the virtual simulation challenges, they get a real physical race car to join Alex and the other teams racing in real life.
Maybe we'll have
maybe
open.
to add to this. I think there is also a chance that multiple series emerge from that. Like if we probably also that open source part can help to reduce the cost of running such a program. And I don't see a reason why there shouldn't be, a university series, open source, or like a community series, or probably OEM series. So I think it's important to somehow have equal play and a level playing ground. So you shouldn't send five undergrads against Volkswagen. That's probably an unfair thing. But I think the technology is pretty open right now. The challenge is to operate it, and if we manage to get the cost down and to make this, or probably not even get the cost down, but to get it in a sustainable, funded way. I don't see a reason why that shouldn't be possible.
Okay, that was a great statement to an amazing talk and an amazing Q&A, Alexander. Thank you very, very much. That was really impressive, and we are really looking very much forward to see you and all the other teams in Las Vegas. Hope there is a live streaming over there, and I hope maybe we can even replicate some sort of event like this and have not to bring you too much away from the racetrack, but maybe just give some impressions. And I would really like to thank you and all the contributors who asked questions from the Twitch stream, and David, Nicholas, Joe, Alexander, and all the guys. Thank you very much. It was a pleasure having you. And I think that has once again demonstrated what a community effort across countries, across borders can achieve. And that was really, it was a great evening. Thank you very much, and wish you all good luck and stay safe. And Alex,
Rainer?
go fast.
Rainer, guys, before you go, for the viewers on Twitch, I have a video of one of the cars. You had a video of your car spinning, Alex. I have a video of a car crashing.
Maybe from my car, I'm pretty sure.
No.
Also, for those that can't make it down to Vegas, Rainer, they can look at Rainer on the DIY Robo Cars Discord channel. Virtual racing on goes, zero barrier to entry. Check that out too.
Yeah.
DIY Robo Cars. And
so maybe as a parting thing is I can show a quick video here. That's the fun one. Ouch. Well, we'll work on making all that better.
So, yeah. Thank you very much.
Thank you, Alex. Thank you, Rainer, Joe,
Bye-bye.
Dave, Nick.
See you. Bye.
See you guys. Thanks, Joe. Bye. See you guys. Thanks, Rainer. Great job.
Oh.
That's the little guy.
Cool car. Yeah.
Yeah, it was. I don't know if you saw the video, but I actually made a video of where the big cars use LiDAR, and this one uses a LiDAR too. So I made a video of
Cool.
where like you can see the two cars together basically. But Reiner,
Yeah, I
thank you
saw
so
that, yeah.
much. You did?
Yeah. Excuse me?
Oh, okay. Reiner, thank you so much for organizing this. This was actually awesome. And let me stop recording at this point. But yeah, thank you for putting this together. I think that was a really